Hello and most welcome to 11, let's see here, 39 it must be, of the Heidegger series. I'll check it out here to be absolutely certain. Sorry about that. $1139, that's correct. It's a bit of a strain today. I would make a strong case here now, and that there is an absolute connection between our bodily movement and our ability to understand. I mentioned earlier in 1138 of the H series that the right hemisphere learns by doing complicated movements. After they are learned, they more and more go to the left hemisphere, and those static movements or already acknowledged movements become what is representations. And this is very good. I've been wondering how to express the word representation. It's very tough, and I haven't been too happy with the description coming from Ian McGilchrist in this case. Although I'm a huge admirer of all his work, there in that point he has not been able to, what I would say, have a good idea what a representation is. But a representation is call it fixed, stored movement without thinking of movement as something taking place in externality. Think of the Klein bottle instead, a movement that is both inward and outward. This has three good advantages in contrast to what Ian McGilchrist usually says. One advantage is definitely that we understand the connection between an imagery, a word, meaning and all that being of the right hemisphere, it's being thinking, whereas the left hemisphere has ready-made movements, representations, understandings. They're all the same thing. There can be no understanding without a new movement. Therefore, so to speak, the left hemisphere puts understanding together with the old pieces, thereby not coming into the right rational mind. And that could also, and that's a second advantage, it's linked now to the heart consciousness of Richard E. Lind and all ancient people in all cultures as it used to be. A connection I've been looking for a very long time. The third advantage is that it also connection to John Appleton's posture, release, imagery. And without the release, so to speak, if that's a good word, there can be no understanding. We'll be stuck in the old understanding. Maybe a fourth way is to help Edward de Bono, who often argue that we're stuck in the old, try to describe everything in the old. Four good advantages. And I'm going to start with an article here and then get into connectivism. But first I'll start with an article because it's of extreme importance to connect connectivity to the body. Otherwise, connectivity won't mean much. It is a fantastic idea, but it needs the body as well. Here is an article that's named From Movement Kinematics to Social Cognition, the Case of Autism. Introduction. Already in the earliest descriptions of autism, a variety of movement atypicalities have been noted, including atypical posture control, gait, upper limb movements, and fine motor controls. However, these neurologically important signs have not been investigated as much as the social impairments in autism. Recent research has significantly advanced our understanding of the contribution of movements to socio-cognitive function. This literature suggests that the process such as action perception, prediction, and interpretation are critical to social communication. For instance, these processes may be facilitated between two individuals who move similarly and impeded between individuals who move differently. In this paper, paragraph 2 briefly summarizes the literature suggesting that autism and typical individuals move differently. Paragraph 3 examines the contribution of one's own movement patterns to the perception, prediction, and interpretation of movements of others. Finally, paragraph 4 proposes that movement differences between typical and autistic individuals may contribute to bilateral difficulties in reciprocal social cognition. If so, autistic individuals will have difficulties perceiving, predicting, and interpreting the actions of typical individuals, and conversely, typical individuals will have difficulties perceiving, predicting, and interpreting the actions of individuals with autism. This interpretation goes some way towards the increasing recognition that roots of the social difficulties that autistic individuals experience are deeply embedded in compromised interactions and are not solely due to the processing defects that are internal to the autistic person. 2. Are movements atypical in autism? Autism spectrum disorder, henceforth, autism is a developmental disorder characterized by impaired communication and social interaction and restricted and repetitive interests. Effects like sluggish reflexes, clumsy gait, and an absence from an early age of anticipatory postures when being picked up. They don't react when they're being picked up. They don't anticipate what will come. While most studies have focused primarily on social impairments in autism, there are also a number of reviews that have focused on movement atypicalities and abnormalities in areas of the brain relating to movement such as the cerebellum, striatum, and brainstem. Here we gave a brief overview of behavioral differences between autistic and typical individuals that have been noted with regard to various different types of movement. Kellner describes actions at 4 non-independent hierarchical organized levels. 1. The kinematic level, the trajectory and velocity profile of the action. 2. The motor level, the processing and pattern of muscle activity required to produce the kinematics. 3. The go level, the immediate purpose of the action. And 4. The intention level, the overall reason for executing the action. This approach is particularly useful in illustrating that, due to the non-independence between different levels of action hierarchy, and atypicality at one level can impact upon other levels. Although both approaches are useful to bear in mind throughout this article, in order to demonstrate that atypical movements are not restricted to one fundamental domain such as handwriting, but may impact on many aspects of everyday life for individuals with autism. Posture and balance. Autistic participants were generally less stable in their posture and typically exhibited a tendency to put most of their weight on one heel too. Similar patterns have been observed in subsequent studies of posture sway. For instance, autistic children demonstrate abnormalities when standing and looking straight ahead, standing while dual tasking, standing with eyes closed, standing on unstable surfaces, and standing on a sway-referenced platform. With a view to investigate the development of postural control in autism, Minshew et al. Recruited the participant ranging from 5 to 52 years. They concluded that the development of postural control was delayed in autistic participants and differed from typical posture control even in adulthood. Gait. At least 7 separate studies have assessed gait, or the style of walking, in autistic children and old adults, and a number of atypicalities have been observed. For example, Nobile et al. Show that, compared with typical individuals, autistic children exhibit trunk postural abnormalities, difficulties in walking in a straight line, a marked loss of smoothness, an increase in the jerkiness of movement, and in general a stiffer gait in which the usual fluidity of walking was lost. In a comprehensive review of gait atypicalities in autistic children, Kindregan et al. Found that the most commonly reported atypicalities concern step width, step and stride length, reduced velocity, increased time in the standing phase of gait, on the basis that increased step width provides a wider base of support and reduced velocity and step and stride lengths help a walker to keep the center of gravity. Within this base of support, they argue that together with these results suggest a tendency for individuals with autism to augment the stability during walking, and therefore that autistic children have a more unstable gait compared with typical children. Extending his research into adolescent years, Weiss et al. Found that 16 to 19 years old with autism differ from typical controls with respect to various spatiotemporal aspects of gait, including step and stride length, foot positioning, cadence, velocity, and step time. Hallett et al. Report mild clumsiness of gait and a reduced range of motion of the ankles in autistic adults. D. Upper limb movements. Paradigms investigating upper limb movements in autism typically measure arm movement in preparation and execution times and kinematic parameters. i.e. parameters referring to joint motions and angles at specific points in a movement, and typically reported in terms of the velocity, acceleration, and jerk of a particular point of the body. Such studies have revealed differences between autistic and typical individuals. To illustrate, Glazebrook et al. Found that adults with autism required more time both during movement initiation and execution for manual aiming movements, while Reinhardt and colleagues have reported that autistic children and young adults require more time to prepare point-to-point movements, that is, moving from one point in space to another. Further work used the reach to grasp task, where upon presentation of a cue, participants move their hand from a start position to grasp a target object. Using such a task, Stewart et al. Found that autistic children and adolescents exhibited longer movement times from the start of the movement to the grasp of the object. Young et al. Found that children with autism showed significantly longer movement times for reach to grasp action and executed their movements with more jerky kinematics. In line with this, Koch et al. Demonstrated that high-functioning adults with autism make more jerky movements that proceed with greater acceleration and velocity, even when these movements are not goal-directed and thus relatively unconstrained. E. Fine motor control. Fine motor control has typically been examined through analysis of handwriting in those with autism. While these studies have generally revealed autistic individuals to have atypical handwriting, the specific details of how handwriting deviates from the norm vary somewhat across studies. In a comprehensive review of the literature concerning handwriting produced by children with autism, Kursky et al. Note consistent atypicalities in the overall legibility of handwriting and letter formation. For example, autistic children have been found to produce more poorly formed letters, though they do not exhibit difficulties in correctly aligning and spacing letters. Macrographica, that is atypically large handwriting, has also been noted in both children and adults with autism. These features have been related to atypical movement kinematics. Johnson et al. Demonstrated that handwriting-related movements were considerably larger, peak velocity was significantly greater, and movement trajectory more variable in autistic children. An analysis of the velocity of movements suggested that autistic children may require higher energy input to achieve the same smoothness of movement as typical controls. Summary. Compared with typical individuals, children and adults with autism have on average been reported to exhibit increased instability during both standing and walking, atypical kinematics with respect to various movements, poor fine motor control as illustrated by atypical handwriting, and when making goal-directed or point-to-point arm movements, increased preparation and execution times. These findings, which are highly reliable and robust over many studies, suggest that at a low level of cognitive processing, autistic individuals are likely to make movements which deviate from those made by individuals without autism. Adopting a bottom-up view, it is plausible that these low-level movement differences might impact on higher-level processing. This does not rule out that separate difficulties also exist at a higher level. However, it is possible that a bottom-up account would result in parsimonious explanation of at least some of the symptoms of autism. In paragraph 3, we consider how the established movements atypicalities may influence higher level processes, such as the perception, prediction, and interpretation of others' action, and how in turn this may disrupt very high level social interaction. Three, movements influence socio-cognitive processes. Perceptual and motor systems are tightly linked. Action influences perception and perception influence action. Research over the past few decades has demonstrated that this reciprocal relationship between action and perception may play a role in a wider socio-cognitive functions, including action prediction, estimation of others' mental states, very interesting, imitation, and the development of positive social attitudes. A. Action and perception. Watching another person perform a movement evokes activity, often referred to as motor resonance, in one's own motor system. Evidence for this claim comes from a variety of fields. Single-cell recording studies have found that neurons in the motor system of the macaque, subsequently labeled mirror neurons, fire when the monkey passively observes an action. And research using a range of neuroimaging methods, including functional magnetic resonance imaging, fMRI, once more, and transcranial magnetic stimulation, magnetoencephalography, MEG, and an electroencephalography, EEG, provides strong evidence for similar responses to action execution. and action perception in the human brain. fMRI experiments have identified overlapping activity for action perception and execution in a network of regions, subsequently referred to as the Human Mirror Neuron System, MNS, including the inferior frontal gyrus, the inferior parietal lobe, ventral and dorsal premotor cortex, anterior intraparietal sulcus, and the superior temporal sulcus. Furthermore, cross-modal repetition suppression, where a reduced response is seen for observation following execution, or vice versa, has been observed in both frontal and parietal MNS areas. Studies using MEG, that is magnetoencephalography, and EEG, electroencephalography, have also shown that sensimotor oscillatory activity in both the 8 to 12 Hz, which is the Mi, and the 15 to 30 Hz, which is the Beta, ranges is attenuated both when observing and executing actions. However, electrical activity is not simply suppressed during action execution, but is modulated dynamically. Correspondingly, studies have demonstrated that sensimotor oscillatory activity is also modulated dynamically during action observation, according to the kinematics of the observed movement. For example, Press et al. Demonstrated that beta power was dynamically modulated according to the acceleration profile of an observed arm movement, mirroring what would be expected during execution of the same action. Such automatic activation of the motor system during action observation can influence behavior, that is, observing others' action can interfere with ongoing action selection and execution, such that we automatically imitate actions we observe. Just as perception influences action, action influences perception. For example, including a motor load through performance of a concurrent task has been shown to modulate perceptual judgments about the weight of an object being lifted by an actor or speed of a walker. Similarly, perceptual judgments can be impaired through the application of disruptive transcranial magnetic stimulation to the motor regions. Wow, I say. Furthermore, in clinical population, deficits in action production resulting from either cortical lesions and or apraxia are correlated with deficits in action recognition. Thus, there is a widespread evidence that motor and visual systems are intrinsically linked and mutually influence each other. B. The importance of being similar. A worked example. Several theoretical accounts of the relationship between the visual and motor systems predict that the more similar two people are in their action execution, the more likely they are to engage in motor resonance when observing each other's action. The following worked example describes such a situation in detail and elucidates how such effects might come about. This example concerns three people, Fred, Jill, and George. When Fred performs a reach to grasp movements, movement, he typically accelerates his hand toward the objects until he has covered 50% of the distance, then begins to gradually decelerate. Dill performs this action with the same kinematics as Fred. George is different. George continues to accelerate his hand forward until he has covered 65% of the distance to the object. Fred has made movements like this for most of his life. He has a wealth of experience of observing his kinematic profile and simultaneously activating the motor codes for executing this reach to grasp movement, i.e., experience of simultaneously seeing and doing. This vast amount of experience means that for Fred, the visual representation of a reach to grasp movement with a 50% acceleration phase has become tightly associated with his motor programs for executing a reach to grasp movement. Consequently, when Fred sees Jill make this movement, it automatically activates his motor codes for executing a reach to grasp movement. By contrast, Fred has very little experience with seeing reach to grasp movements that follow George's unusual kinematic profile. Thus, for Fred, the visual representation of reach to grasp movements with George's kinematics is only weakly associated with his motor code for executing a reach to grasp movement, and therefore George's movement only weakly activates Fred's motor system. George's movement only weakly activates Fred's motor system just by seeing. Wow. It can therefore be seen that movement